Using a lot of power today. See, I can write down the Jordan canonical form immediately because I know that the number of blocks is just this number right here. There's only one block. I've got my lambda, so we just write down the JCF right there. We just literally write that down. And then, see, the way you're going to solve this equation, let me just remind you, I was telling you about this in the review, is you're just going to replace this system with the easier one, y prime equals jy, and then once you've solved for y, this equation will take you back to x, right? That's kind of the idea behind it. If you don't believe me, let me just make sure you understand where that's coming from. See, basically you just take this equation and you take out the a and you say, you know what, a is the same thing as qj q inverse. And then you left multiply by q inverse, and you get that, right? So it's literally, and then you just basically, you just call this y. So y prime equals jy, right? And then if y is equal to q inverse x, well then x is equal to qy, just by rearranging the equation. So that's the key. These are the two key things right here. Okay? So I do need to find the q. So why don't we just go ahead and oh, by the way, do I need to find the q inverse? Does it show up anywhere?
No, it doesn't.
That's awesome. We don't have to find q inverse. We just have to find q. Okay, so, well, on a 2 by 2 it wouldn't have been that bad because we know how to find the inverse of a 2 by 2. But we don't even need to work that hard. So let's just find Q. Q is the matrix whose columns will be the vectors in the cycle, gamma. So we need to do that whole cycle thing. What side or what length of a cycle are we expecting? 2, okay? So it's going to look like V, and then A minus 3I times V. Well, here is A minus 3I. By the way, what is the square of that matrix? And you, by the way, you cannot row reduce this. You just have to live with the matrix as is. You square that matrix, you are going to get 144 minus 144. Negative 108 plus 108. These cancel. And these cancel. It's all 0, right? So the square of the thing is 0. You couldn't get a cycle of length 3 even if you wanted to, because the square of the matrix is already 0. So this is as good as you can do. You're looking for a vector that will survive this matrix, right, but not survive this matrix. Well, no vector will survive this matrix, so you really just need something that will survive this matrix. What's an easy choice? 1, 0. I like it. Just pick something simple. 1, 0. And when I multiply 1, 0 times this matrix, actually, could I choose a different one? Just so I'm using my notes in case I screw up. I'm going to choose 0, 1. It's just a little cleaner to not have negative signs flying around. If I choose a vector 0, 1, then what is A minus 3I times 0, 1? Exactly, 9, 12. Am I free to row reduce that to 3, 4? No. So even though we wrote up here, by the way, this is an eigenvector. You'll notice it's a multiple of this one. But you cannot take this answer and reduce it to a smaller one. You have to live with whatever this comes out to be. But now, that is your Q. Q is a 9, 0, 12, 1. Just like that. That is Q. So got that. And we've got J. So at this point, we are ready to go ahead and finish things up. We need to find this, we need to solve this simpler system. So what we're going to have now is y1 prime, y2 prime equals, and what's it going to be? Here's j's right here. So 3y1 plus y2, and then y2 prime is going to be 3y2. Look all right? Actually, it would be better if I write it with the 3y2 like that. So you see 3, 1, 0, 3. That's your J matrix. This is really just writing out this formula here. Okay. Which of these looks easier to solve? The bottom one doesn't have any y1s in it, so we can just solve it directly. Anybody know a function whose derivative is equal to 3 times itself? Exactly. E to the 3t, right? So, and then there could be a constant in front of that. I guess I want the general solution. So I'll say c1 e to the 3t. Okay? Now see, if the matrix had been diagonalizable, then all of your functions, y1, y2, and so on, they would all just be that simple. It'd be that easy. You just take these scalars and put them in the exponents there. Okay. Unfortunately, this one was not diagonalizable, so the first differential equation, even after we simplified it, it didn't come out quite as nice. So here's where what we're going to do at this point is treat the first equation like as a first order linear equation. So it's y1 prime minus 3y1 equals c1 e to the 3t. That's the way you want to rewrite a first order linear equation. We're going back to 250b a little bit here. I'll probably do one of these in class tomorrow. The one I do in class tomorrow I might do a 3x3. But anyway, just to practice it once for you guys. Does anybody remember how you solve first order linear differential equation?
You put e to the
Because
You need an integrating factor.
e to the integral of p of x.
Right, right. And the p is the coefficient in front of the unknown function here.
You have p and then you have a q of x on the other side.
Right, this is the q of t over here, right? So we have that. So this is just e to the integral of negative 3 dt. So this is e to the negative 3t. And when you're doing the integrating factor, which I call capital I, you don't have to put a plus c on the end of that. Because you're only looking for one specific antiderivative. Okay, then what happens on those first order linear equations is you get the integrating factor, e to the negative 3t, times your unknown function, which is y1 at this point, quantity derivative is equal to, and then what goes on the right-hand side of the equation is you take whatever the original right-hand side of the equation was and multiply it by the integrating factor. Ooh, so c1 e to the 3t is going to get multiplied by e to the negative 3t. So this times this, right, is just c1. Now we just integrate both sides. So we're going to get e to the negative 3t times y1 is equal to c1, the antiderivative of a constant is just a constant times t plus another constant, which I'll call c2. And so y1 of t, if I move the e to the negative 3t to the other side, it's going to become e to the positive 3t. So it will be e to the positive 3t times c1t plus c2. So there's y1. And then finally, we already wrote down y2, which was just c1 e to the 3t. I did it right. Let me just make sure I see it's right. I think that's right.
Are we going to have to do this on Wednesday?
Maybe. It's not so bad. Yeah, I know. It's just a slight extension of what we did in for the diagonalizable case. And it is building off of 250b. I know I haven't really covered it in this class, but I'm covering it tomorrow. And I know that's a little last minute, but it's such a small extension of what we do for diagonalizable cases. I didn't think it would be too terrible, hopefully. Let me just make sure this is what I actually got. Well, that's what I got for y1 and y2, but am I done yet?
No.
No, I'm not. I have to multiply by q to get x, right? So this is y1 and y2, but then we have to find x. Let me not erase the q. So then, basically x1, x2 is equal to 9, 0, 12, 1 times y1 and y2. So that would be e to the 3t times c1t plus c2, and then c1 e to the 3t. Okay? So we just have to work this out. It's going to be 9 times e to the 3t times c1t plus c2. And then it's going to be 12 e to the 3t times c1t plus c2 plus c1 e to the 3t. So now let me check the answer. Make sure that's what I actually got. x1, c1, okay, plus 9 c2 e to the 3t, c1 e to the 3t, 12t plus 1 plus 12. Yep, that's it. That's the final answer now. The thing I like about this type of problem, actually more than the Markov chain problems, is, at least for a test situation, you don't have to ever take the inverse of anything. For the Markov process, you've got to do the q and the q inverse. But here you don't even have to do the q inverse, you just have to do the q. So, it's just a very slight extension right here to do this first differential equation, but it's beautiful, isn't it? That now, because we have this Jordan canonical form concept, we have a nice way of solving these systems. So, you might kind of feel like it's new material. I don't like to think of review sessions as being for new material, but since I am going to actually do it tomorrow, I'm kind of giving you guys a preview now, if that makes any sense. Okay, questions on that? Be scared.
I still don't understand how you got the y prime and the x over there in the Q1. I don't understand how you got from x prime is equal to a times x.
To these two?
Yeah.
Oh, that.
I know you erased it and I wrote it down, but I still don't understand it.
Yeah, let me just show you one more time. That's actually no different than it was when we did it for the diagonalizable case in the notes. Because basically all that you're doing is taking out the a and you're replacing it with qj q inverse. Now in the diagonalizable case it would have been a d in the middle, but otherwise it's the same. And then we left multiply by q inverse, so we get q inverse times x prime equals j times q inverse x. And then we take q inverse x and we just call it a new name because it is, after all, just another vector. So I just take q, this is like a matrix times a column. It just gives me another column. And then what you have right here happens to be the derivative of that column. So you end up with that equation. And then, because I called y q inverse x, then x is qy. It's really, it's just a lot of notation, really, that's in there. So, it's notation that we ourselves have created. It's not like it's part of the theory that has to be that way. Okay, I have just a couple more really quick ones and then we're going to call it a night, if that's okay. You guys still awake? You're just very low in your chair. Almost on the ground. I wanted to do, okay. Couple of really quick true false. Now, I'm not going to ask you true false on the test per se. I'll tell you if it's true or if it's false and ask me to give me a justification. But I want to run a couple of these by you. So this is number 7, part A. here it is. If the Jordan canonical form of A is equal to J, then, and this is true or false, sorry, true or false. If the Jordan canonical form of A is equal to J, so then think about what would be a Dr. M kind of question. The Jordan canonical form of A squared, is it equal to J squared? Well, that's a good question, I guess, hopefully. So if you have a matrix and you find its Jordan canonical form, then is it true if you square the matrix that its Jordan canonical form is the square of the Jordan canonical form of the original matrix? Would J squared be equal to J? Was that always going to be true?
I guess it would be. What would J squared be equal to?
Maybe we should think of it as an example.
The square is the diagonal.
Well, if the Jordan canonical form, okay, if the Jordan canonical form of our matrix happens to just be a diagonal matrix, then when I square that, I just square the diagonal, right? And basically that would be true then, right? Because what are those diagonal entries? Those are just the eigenvalues. So if you take the eigenvalues of A and you put them on the diagonal to get J, then the eigenvalues of A squared, aren't those just all of the lambdas squared? So then the Jordan canonical form would still be a diagonal matrix with just all of the squares of those eigenvalues on the main diagonal. So in that case, this seems to be that it would be true. If J is a diagonal matrix itself, then we would expect that this is a true statement for that. Statements, okay, so if I asked you something like this, I would probably be asking it to you, not assuming that you actually thought about this problem before, right? Because I haven't shown it to you before. So I want you to pretend right now we're taking the test and you see this question, right? I have not asked you this question before, so that means it must be something that you can think about and do kind of on the fly. It's not going to be something that requires a lot of heavy, deep thinking and putting a lot of things together, right? It might be helpful to really keep it simple here. So if we're talking about matrices, I mean, I guess you could say, all right, you might think about doing this. So you've got Q inverse AQ equals J. That's kind of the standard format, right? So then, if I sort of square both sides of this, so this is something we can do, right? What do I get here? I get Q inverse times A squared times Q equals J squared, right? Because the Q inverse and the Q in the middle, they cancel. I've kind of seen this kind of thing before. So A squared is certainly similar to J squared. They are similar to each other. So if they're similar to each other, then as long as this is in Jordan canonical form, then it will be the Jordan canonical form of our matrix, right? But my question is, so, okay, if I square a Jordan canonical form, let's think about a 2 by 2 matrix, very simple. And let's take a Jordan canonical form, and let's take the sort of the worst case. The case where we don't get a diagonalizable situation, but rather we get a block, a 2 by 2 block. Suppose that's my J right there. Some eigenvalue twice with a single block, so it's a 2 by 2 block. Now what do you get when you square that? get a squared, a plus a is 2a, 0, and a squared. Is that in Jordan canonical form? Jordan canonical form, okay, it's clearly a 2 by 2 something, right? With the eigenvalue on the main diagonal, that's fine. But what has to be on the super diagonal of a Jordan block? A 1. So as long as a is not a half, as long as a does not equal a half, this doesn't work, right? So if I took a specific example, so if, let's just say we took a, hey guys, as an example, what if a was just equal to j? Let's just take that. Let's take a equal to 1. There's a Jordan canonical form with one 2 by 2 block, right? Then when you square it, you get 1, 2, 0, 1, according to this, right? And that's not in Jordan canonical form. So this is false. It's false. Make some sense? Okay, let me give you just a couple more. I'm having too much fun with this, as you can tell. I just want you to have a taste of like what level type of thinking would I ask you to do. And something like that, maybe is reasonable. With something like this, I would probably give you a choice. I'd give you like 2 or 3 of these and say, pick 1 or 2 or something like that. I would make you do a ton of these. Here's another one. B. If capital A, which is n by n, is nilpotent, does anybody know what that means? I didn't think so. Okay, I was waiting for somebody to ask me. So i.e., I'm going to tell you what it means. A to the k is equal to 0 for some power k greater than or equal to 1. And again, this is still true, false. True or false, that then 0 is the only eigenvalue of the matrix capital A. Is 0 the only eigenvalue? By the way, this matrix, I think you'd all agree, capital A cannot be invertible. Because if the matrix was invertible, then no power of it could be 0. I mean, just think about the determinant here. The determinant of A to the kth power is 0, so the matrix is not invertible. If a matrix is not invertible, what do you know about the eigenvalues of a matrix that's not invertible? If my matrix is not invertible, would you agree that at least one of my eigenvalues has to be 0 to make the determinant 0? But what we're saying here is even stronger. We're saying 0 is the only eigenvalue, that these all have to be 0. Right? That's kind of what it's saying.
Based off of that, doesn't that tell us that we don't have to have only 0 in that eigenvalue?
For a matrix that's not invertible, you're right. We could have some eigenvalues that are 0 and some that aren't. But we're assuming an even stronger type of matrix. It's not just does it fail to be invertible, it's actually nilpotent in the sense that there is a power of the matrix that actually becomes 0. Right? So that's actually kind of the key to this. So really the thing you need to do here is kind of remember where all of this eigenvalue, eigenvector stuff starts from. So if lambda is an eigenvalue of A, then there has to be an eigenvector, a non-zero eigenvector that makes this equation true. Right? AV equals lambda V. So let me ask this. So and lambda is my eigenvalue. The question is, must lambda be 0? Well, what would a to the kv be equal to if av was equal to lambda v? Like that, right? Because it's just a of a of a of a of v, and every time you apply a, you basically